Now, so far in this film, we've discussed only one of the basic things we can do with the electronic tube. We can use it to rectify. The second basic thing we can do with it is amplify. Here's how. Between the cathode and the anode of the two-element tube, which we diagrammed a while ago, we now place a grid. To this grid, we connect an input of some weak voltage which we wish to amplify, perhaps that of a faint radio signal from halfway around the world. Now let's see what happens. Every time a negative potential is impressed on the grid, even though it be very minute, it has a large effect in reducing the number of the negatively charged electrons which would otherwise keep flying from cathode to anode. Conversely, when the grid is positive, an equally large effect is exerted in increasing the flow of electrons from cathode to anode. The important thing to note here is this. A small amount of power applied at the grid is amplified into a large amount of power in the anode or work circuit. This amplifying property of the three-element electronic tube is put to work in innumerable ways. Westinghouse electronic amplification now helps provide radio and radio telephone contact between airplanes and control stations on the ground, between ships and their communication bases, both afloat and ashore, between individual tanks and their tank force commanders, between firing line and headquarters, between seadrome lights and night-flying pilots who can turn them on by radio signal. In the field of power engineering, electronic amplification permits the measurement and analysis of minute voltages, stepping them up to the point where they can be seen and interpreted on oscilloscopes. When this giant rotor is completed, its precise dynetric balancing will be made possible by amplifying tubes. Testing of these propellers for vibration fatigue will also be facilitated by electronic amplifying tubes. Up to now, we've considered two of the basic things that the electronic tube can do. It can rectify, it can amplify. A third thing it can do is generate. The term generate in this connection is meant in a general rather than a technical sense. A triode is connected for oscillation in the way shown here. The system then becomes capable of changing direct current into alternating current. Note that what we're doing in this case is amplifying in the usual way and then feeding back to the grid part of the amplified voltage. Continued repetition of this feedback results cumulatively in a strong alternating current. This electronic means of generating alternating current is important because it can produce very high frequencies, frequencies up to millions of cycles, far beyond the range of ordinary rotating equipment. A familiar application of this is the radio transmitter. This modern transmitting room of Westinghouse station KDKA is a far cry from the pioneering equipment of its famous predecessor. This scene reproduces an historic occasion, the first time a radio transmitter was used for large-scale public entertainment.
This is station KDKA of the Westinghouse Electric and Manufacturing Company. We are about to begin the reading of the presidential election returns between Warren G. Harding and James M. Cox. Stand by, please.
Here is a new, less familiar application of electronic high-frequency generation. High-frequency heating of 200,000 cycles per second is now used to flow tin as the final step in the electrolytic plating of steel strip. After steel strip comes from its electrolytic tin plating bath, it first passes through a washer, then between hot air drying jets. At this point, the steel strip has a coating of tin that is relatively dull and porous. Next comes a vital step. The strip is raised to the top of the heater unit housing, inside of which is a series of high-frequency coils. As the strip comes down through these coils, induced electric current causes heat, which flows the tin almost instantaneously, greatly improving its structure as a protective covering. Here's the result. Tin plate that is mirror smooth, free from porosity, so perfect a protective covering that 1 pound of tin can now do the work of 3. Note the horizontal bars in this close-up. These are parts of one of the high-frequency coils that affect the tin flow. If you look closely, you can see the difference in texture between the porous tin entering the top of the coil and the shiny flowed tin leaving at its base. And these are the tubes that generate the high-frequency current which makes the entire process possible. Another important result of this new Westinghouse electronic process is time saving. Tin can now be flowed at a rate of more than 1,000 feet a minute. Here's another example of where electronic high-frequency generation is doing a job today. Dielectric bonding of plastic and plywood sections in a matter of minutes instead of days. As a result of this application, plywood-constructed PT boats can be produced more speedily. Dielectric heating also cures intricate plastic forms faster and better. Here, a dielectrically cured plastic piece is being given a stress analysis. Carrier current relaying also applies the electronic principle of high-frequency generation. Here's part of the equipment that does the work. This equipment makes possible an enormous increase in the speed with which transmission lines can be cleared of faults. Its effect is to increase the load-carrying ability of a system up to 50% or more. We've now illustrated three of the basic ways that the electronic tube can be put to work. It rectifies, it amplifies, it generates. And here's a fourth thing it does. It controls. This diagram illustrates one of the principal mechanisms of electronic control. We use the grid here not to amplify a weak signal, but to control the flow of power to a machine. To do this, we connect the control circuit in such a way that it becomes a function of temperature, speed, time, or any other variable. As a result, grid potential is varied, and the work circuit is automatically closed, modified, or opened. And we can do all this with split-second timing and incomparable precision. Take, for instance, this electronically controlled spot welder. Without sound, without friction, without flame, electronic control on this equipment makes and breaks contact with split-second timing. Seam welding, too, is electronically controlled. As a result, plane parts today are being literally sewn together with electric current as thread. But welding, of course, represents only one opportunity for electronic control. Automatic stepless regulation of motor speeds is another application. Without the smooth acceleration which such control makes possible, delicate materials, such as the capacitor windings being handled here, might be broken under the shock of starting and abrupt speed changes. Now for still another basic thing that the electronic tube can do. It can also serve as a bridge to transform light into electric current. Here's how. We replace the ordinary heat-activated cathode of a two-element electronic tube with one made of photosensitive material. Light can now replace heat as the stimulator of electronic emission. The stronger the light, the greater the electronic emission, and consequently, with the aid of an amplifier, the more power flowing through the work circuit. This is important because it means that photoelectric tubes can function as light relays and so be given an almost infinite variety of jobs to do. Scanning the soundtrack of the talking motion picture film you're listening to right now is one of them. Another is the television camera. The iconoscope used in this camera is merely a special form of electronic tube. Product and process control is still another application. In this plant, a phototroller automatically stops a conveyor belt every time a lightning arrestor comes to its point of inspection. Here, a Westinghouse electronic eye inside the metal housing spots pinholes in metal strip as it comes from the rolls, automatically operating a relay that rejects defective sections, dropping them out of the production line without a moment's loss of working time.